Sorry. So I'm going to talk to you today about galaxies like these, kind of spiral galaxies that are nearby. So we have a new survey of disk galaxies that is called the MUSE Atlas of Disk Galaxies, which we have abbreviated as MAT. And this is a survey with MUSE. The PI of this survey is Marcella Carollo, and a lot of the work that I am going to present today is actually done by Santi Eros Ferrer and Martina Fagioli and myself. Also, Joanna Wu and Sandro have been involved in this survey. So let me first tell you something about MUSE. So MUSE is a new IFU instrument on ESO VLT, and it has an enormous field of view. It's 1 by 1 arc minute, so this is slightly smaller than the size of an HST image, and it also has a very nice long wavelength coverage from 4700 angstrom to 9300 angstrom. So we get a lot of lines for local galaxies. So there's H beta, H alpha, lots of stellar absorption lines, and indeed you don't have to use this instrument just to observe far-away Lyman alpha nebulae, but you can also use this for nearby spiral galaxies. So there's a very nice spectral resolution, so it's 2.5 angstrom over the full wavelength range, which sort of translates into 2000 at 4600 and 4000 at around the calcium triplet. One of the exciting things is that in the near future, ESO will install AO unit for this instrument, which means that at least for the wide field mode, we're going to get spatial resolution of 0.3 arc second, and I don't think any other instrument is capable of doing that at the moment. So this is going to be AO in the optical. Okay. So one of our goals with this survey is understanding why spiral galaxies or why galaxies in general are on the main sequence. So we've been selecting 100 targets that are on the main sequence. These are all based on being nearby and having a certain effective radius that fits so that it fits the field of view. And so we started getting data a little bit more than a year ago. Right now we have 25 galaxies. The final goal is to get around 100 galaxies. And what we want to do with these galaxies is study how does local enrichment of gas happen. So you can look at the gas metallicity and see if you see enrichment happening. Can we see inflows and outflows in the gas? For example, if we look at emission lines in our galaxies, we very often see two components present. So there's one narrow component for a line, but very often also a broader component, which might be an outflow or shock or something. How do low and high angular components form? So how do we form bulges? How do you form disks? And can we see accretion of mass? And also we think that this might be useful input for physics in simulations. So far we have 25 of these galaxies observed. They have a mass range of in between 10 to the 8 and 10 to the 11. And we're getting like 7 or 8 targets more before AO, but the plan is that the rest of these galaxies will be observed with AO. So Duncan Forbes had a very nice figure of merit for IFU surveys where he plotted how far out you go in a galaxy versus the spectral resolution, and I think we're doing very bad there. We're relatively low spectral resolution, and we're just probing a little bit more than one effective radius in most galaxies. But what I'll try to argue is that we can actually do interesting things with this survey. So this is one of the galaxies in our sample. This is NGC 1309, and it's the galaxy at 30 megaparsec. This is the MUSE field of view, and just for comparison with other surveys that have lower spatial resolution, if you imagine that one of those boxes is has a resolution of 1 kiloparsec, so this distance here is 8 kiloparsec. You're actually losing a lot of detail. So these are two spectra that come from the same area, and you can see that one of them is very much dominated by emission lines, whereas here you see a lot of stellar, you see almost no emission lines, but just stellar absorption lines. So we think that resolution is actually very important. We have a reduction pipeline for all the galaxies. So we have a reduction pipeline in place. We have reduced the 25 galaxies so far. We also have a lot of analysis tools for determining emission line physics and determining the star formation histories of the galaxies. And let me now tell you something about the ionized gas. So this is an example for one galaxy, where for each Voronoi bin, so we have to bin the galaxies to get high enough signal to noise for the stellar populations, where for each bin we determine these line ratios, and we can say if certain areas are star forming, or if they're composite area, or in this kind of AGN area. So we've done this now for all our galaxies, and you can see that there's a variety. So this is again these line ratios, and they're colored by effective radius. So yellow is far out, and purple is close to the center. So you can see sometimes purple is related to shocks or AGN activity, but it's not always the case. It can also be in different. You can also have star formation in the center. So one fun thing that you can do is you can now map this back on your original galaxies and see where these things are. And so you can, here we've color-coded these maps by if the gas is excited by star formation, if it's composite, or if it's AGN or shock dominated. You can see a wealth of structure. For example, here you can see that it traces a ring or spiral arms. Here something similar, you can see this kind of spiral structure, or maybe it follows the bar here. So there's a lot of information here. We're still processing this. There are no big results yet to give. One of the things you can do is you can take for in this case this galaxy NGC 5006, we can take the star forming gas and we can take the shocked gas, and we can look at the kinematic properties and try to relate those. So what you see if you look at the velocity field, you see nice rotation both in the star forming gas and in the AGN or the shock dominated gas, which basically tells you that the gas is just following the potential. But if you start to look at the velocity dispersion of this gas, you can see that here this is kind of blue, which means that it's 30 kilometers per second velocity dispersion, which is very close to the instrumental resolution, or it's actually below the instrumental resolution. So this might be even narrower. If you go to the shock dominated areas, you see that it's much redder. So you can see differences now in also the kinematics of the gas. That is sort of shown here as a function of effective radius. You see that the star forming gas has a lower dispersion than the shocks. This is another example where this is even more dramatic. So doing the same exercise now for this galaxy, again you see a velocity field here. Here the velocity field is already a mess, and sigma here is very low, except in the center here, where it goes up to 150 kilometers per second. And this is even beyond the velocity dispersion of the star. So this gas is clearly not these are clearly not gravitational motions. This is really gas being excited. So one example of local enrichment of gas is this galaxy, where we see a very nice star-forming ring right at the center. So if you look at the gas phase, the gas metallicity, you can see that it's green-bluish everywhere here, except here in the center. And here it's enriched. If you then look at the dispersion, you see the stellar velocity dispersion, you see a dip in the dispersion, and you see very young ages. So we know that this is a ring or a disk that is now forming stars. And you can nicely see that this gas is richer. But this has happened here because we don't see any enriched gas out there. So you can do something similar for the by looking at the stellar populations. We can split stellar population in young stars and old stars. So we determine star formation histories for every pixel or vulnerable bin in our galaxies, and then we can look at the dispersions. And very often we see these kind of young stars very close to the center, where also the dispersion is lower. So you can see here that the dispersion is lower for these stars, and we think that these are young disks that are being formed inside bulges. Yeah, so this is another way of showing this. This is velocity dispersion for all the galaxies versus stellar surface mass density, and you can see that not always does the highest velocity dispersion coincide with where your surface mass density is highest. For example, you see this kind of sort of going back to the left corner. And if we look at the velocity fields of these kind of objects, you see that they're, so this is the stellar velocity field. You very often see this kind of small inner disks. So we see that bulges are still forming stars in the center. So somehow gas is getting there. So what about the outer disks? So we're basically determining star formation histories at all locations in our galaxies, and the information that you can get out is shown here in these maps. So this is for one galaxy, where we've now determined the ages or the stars or the amount of stars that have ages that are higher than 5 gigayears, between 1 and 5 gigayears, and lower than 5 gigayears. And by doing some kind of bulge disk decomposition, we try to infer the scale length of the disk component of this galaxy. And if you do that for this particular galaxy, so you measure what is the scale length of this thing, you find that something that is almost independent of redshift. So we've done this for the whole sample now. So you basically look at these are all the sort of the integrated stellar surface mass density profiles. These individual lines are individual profiles. So we fit disks to all these different profiles, and what we find is something that goes roughly as 1 plus z to the minus 0.6. So this is flatter than for dark matter halos, but apparently it's consistent with what other people have seen, something that is going not as steep as 1 plus z to the minus 1. So this is the end of my talk. So we have a very nice new survey with MUSE. We're still trying to interpret all the data because it's really a lot of data. So far we already have 25 galaxies, but in the end we're going to have 100 galaxies. This survey is really a good opportunity to study galaxy physics, particularly for galaxies on the main sequence at the highest resolution. And we have some first results. Most of these are preliminary. We need to do simulations to back things up. So we see feedback in the gas. We see local enrichment of the gas, and we think that the disks build up like this. So, thank you.
The last one of the plots you showed, I think it was 6508, would be classified, that one there, 5806, sorry, as a pseudo-bulge by people like John Cormandy, Fisher, and Drury, because the bulge is elongated. And you could also measure Sirsics, and you'd probably determine that has a fairly low Sirsic. It would be very useful to clarify this story about classical bulges versus pseudo-bulges if you grouped your galaxies into those two categories. Have you tried to do that?
Not yet. Not yet, but it's certainly something that we want to do. maybe this galaxy also has a classical bulge, and this might just be some inner disk that is forming recently.
Well, it's not clear to all of us that this classification of classical versus pseudo even makes sense.
Yeah.
But the kind of data you have would really clarify how these things are forming and what they really are. So
Right.
that is very helpful.
Right. Sure. I mean, that is certainly something that we can do. Whether that will help whether that will lead to a more accurate definition of pseudo bulge, I don't know. But for sure, we're going to try to see how these centers form. Yeah.
Yeah, so I had a naive question about how this high resolution might help us understand the nature of the formation of bars. Like, for example, could you have enough resolution with velocity dispersion to see angular momentum transfer from the bars to the outer parts of the galaxies?
I'm not sure. But for sure, we're very limited to the centers. A good thing is that a fair fraction of, like more than half of the galaxies in our sample actually has bars. But I'm not sure if it's easy to do this.
So just there's a couple things. I mean, first of all, it's 90,000 spectra per shot, right? With MUSE.
It's 300 times 300.
Yeah, so 90,000.
Yeah.
So when you say, oh, we did some pipeline, that's really 2 million spectra that you guys reduced. I'm just, just to put this achievement in context, this is really a heroic achievement. So I'm super impressed. Two things. So you've got the shock line ratios. I'm assuming that you mean that they're probably shocks rather than all AGN.
Yeah. Most of them
so
are.
Then that's probably a pick. And then what was neat was that it was super widespread, and that's going to throw off our star formation rate indicators because we've kind of assumed all that gas. We just take an H-alpha image and say awesome, but it's not awesome. It's actually shock-dominated gas, and so we might want to think about that differently.
Yeah.
Then what are those little? It looks like the bulges were rotating at a different plane for some of them. Now I suspect you cherry-picked. No, that was the one you just showed. Yep, there. So you've got, now I know you've probably cherry-picked those, but how often is that kind of, because that looks like an elliptical galaxy.
Which
velocity field. Actually, all the ones with the little kind of,
these
the kinematically decoupled cores.
Oh,
right? That's what you'd call them in a...
Yeah, well, a lot of these things have bars, and what you see then is that
So this is the bar velocity field. Ah, interesting. Okay, very cool.
Nuclear star clusters have sizes 10 or 20 parsecs. Do you have the spatial resolution to isolate them and then say something about their stellar pops and kinematics?
For sure, for a few galaxies. We actually have one galaxy, 4592, where we see a double nuclear star cluster. And we can model the kinematics, and it looks like these are two clusters that are actually spiraling to the center.
Right.
So I'm really excited about this.
Fantastic. Yeah, lovely data. It's great.
Okay, better move on. Thank you very much, Mark.